it is this picture. So hence the mean velocity of the flow should have been taken into consideration. This is very important. Now in the last I will discuss 3 of the applications of Bernoulli's theorem. Till now we have studied what are the different type of heads and energies and what is the Bernoulli's theorem. The total energy remains constant throughout the section. Now how this can be applied to different equipments, we will see. The 3 important applications of Bernoulli's theorem are the Venturi meter, Orifice meter and Pitot tube. The first one, Venturi meter. A Venturi meter is a device which is used for measuring discharge of a liquid or a fluid flowing through a pipeline. So this particular Venturi meter, it is for measuring the discharge of a fluid. It is named after the Italian engineer Venturi meter. Venturi meter is the name of an Italian engineer in 18th century, and the working principle of Venturi meter, it is based on Bernoulli's equation. And what is Bernoulli's equation? Repeating once again, that the total energy of the fluid particle remains the same for an ideal incompressible fluid flowing from one section to another section in a continuous stream. So this is once again the repetition of Bernoulli's equation. Now we have 3 different type of Venturi meters: horizontal one, the vertical and inclined one. We will see how Venturi meter looks like, the construction of Venturi meter. Basically it has 3 parts. Venturi meter has 3 parts. As you can see here, this is a figure for the Venturi meter. It has 3 parts. The first one is the converging part, second part the throat, and thirdly the diverging part. As you can see, from here to here, from this section 1,1 to here, this is a converging part. Now from this line 1,1 till here, this is the Venturi meter, having 3 parts. Repeating it once again, the first one is the converging part, the center part is throat, and this third one is the diverging part, as it is mentioned here also. This arrow from here to here, it is converging part, the center portion the throat, and the third one is the diverging part. Now keep in mind, the diverging part is 3 to 4 times longer than the converging part. As you can see, it has more length. The converging part is smaller. It is 3 to 4 times longer than this converging part. Let us suppose at section this 1,1, d1 is the diameter, p1 is the pressure intensity, v1 is the velocity, and z1 is the datum head, the potential head, and a1 is the area of this pipeline here at section 1,1. And similarly at this section 2,2, d2, p2, v2, z2 and a2, these are the diameters, pressure intensities, velocity, datum head and area at this section, at section 1,1 and at section 2,2. Then if I want to calculate the discharge using this Venturi meter, I'll have this formula: Q, the discharge actual, is equal to CD A1 into A2 under root 2GH upon whole under root A1 square minus A2 square. Now this is a formula for the, or an expression of the actual discharge through Venturi meter. So we can use this particular formula to calculate the discharge by Venturi meter. So here H is the difference of pressure heads at 1,1 and 2,2 section. Now this is a new term here, CD. CD is the coefficient of Venturi meter. It's also called coefficient of discharge, and its value is always less than 1. It varies from 0.96 to 0.98. Now due to variations of CD, Venturi meters are not suitable for low velocities. Now this is again a limitation of Venturi meter. We can calculate the discharge by this particular formula, but in the case of low velocities, since this CD varies a lot, there is a great variation, so it is not suitable for very low velocities. Now coming to the second application, the orifice meter. Orifice meter is the simple device used for measuring the discharge of a fluid. Once again, this orifice meter is also having the application of calculating the discharge of a fluid. Venturi meter is also used for the discharge measurement, and same is the case of orifice meter, but this device is comparatively very cheaper than the Venturi meter. It is a very simple device, and the working principle, once again, it is based on Bernoulli's theorem. Now how it looks like: orifice meter consists of a flat circular plate just like your compact disc, and it is having a central circular hole. Look at this. This is just looking like a compact disc, but actually this is an orifice meter, and it's a flat circular plate having a hole at the center part from where the fluid passes through it. Now the diameter of the orifice, now this is orifice, this is called orifice. It varies from 0.4 to 0.8 times the diameter of the pipe. Whatever will be the pipe diameter, the diameter of this orifice is, preferably it is half of the diameter of the pipe. It is 0.5 times. And to calculate the discharge through this orifice meter, once again I will have an expression Q actual equal to CD AO under root 2GH upon under root 1 minus bracket AO upon A1 whole square. Now in this expression of discharge, there is a new term AO. Now this AO is the area of this orifice. If we know the diameter or radius of this orifice, this AO can be calculated by applying the formula pi upon 4d square, so it can be calculated very easily. And finally we will get the expression for discharge. Now coming to the third type of application of Bernoulli's theorem, it is the Pitot tube. Now this is very interesting. Using the Venturi meter and orifice meter, we are measuring the discharge of any fluid. Now it is also required to calculate the velocity of a fluid. Many of times it is required. As you can see, this is an attachment at the bottom of an aeroplane. It just looks like a Pitot tube. We will discuss this later, but what exactly is the Pitot tube? It is a tube which is used to measure the velocity of a flow at any point. The main function of Pitot tube is to measure the velocity of a flow at any point in a pipe. So it is not concerned with the discharge part, but it is concerned with the velocity part. So it is a tube bent at right angles. As you can see, the right angle tube, L in shape, the mirror image of L. So this tube is called Pitot tube. Now it works on the principle that if the velocity of a flow at any point becomes 0, the pressure increases at that point. Now this is the basic fundamental working behind the Bernoulli's theorem, that if the velocity of a pressure at any point becomes 0, the pressure increases at that point, or in other words we can say velocity V is inversely proportional to the pressure. Now regarding the construction of this Pitot tube, this is called the stem of Pitot tube. This is the free surface level. It is a view of a river, you can say. This part is called the nose of the Pitot tube. Suppose the flow of the water is towards the right hand side. These arrows are showing the upstream part, the flow. The water will enter into this Pitot tube. This is the body of the tube. When it raises to certain height, this height is h, and from free surface level to the bottom of the Pitot tube, it is h1. So, if I want to calculate the velocity of this flow of water, it can be calculated by Cv under root 2gh. Now, this h, as I have just discussed, it is the height from this free surface level to the top of this level. Cv here, once again a new term, Cv stands for coefficient of Pitot tube, coefficient of velocity. So, by using the formula Cv under root 2gh, I can calculate the velocity of the flow by this Pitot tube. Now, taking a practical application, this is a Pitot tube type attachment at the base of the aeroplane, and during the flight of an aeroplane, if it is required to calculate or to know the velocity of the air, it is a very important aspect for the pilot. So, it can be used to calculate the velocity of the air. So, you can see here that how important this concept is. By using this attachment in the aeroplane, we come to know regarding the velocity of the air. So, this is all regarding the Pitot tube. So, these are the three different applications which we have studied today. The first one is the Venturi meter, the second one Orifice meter, and third one the Pitot tube. So, this is all regarding today's lecture of Bernoulli's theorem and its application. So, to conclude my lecture, I would like to refresh what we have studied today. We have started up with the different types of flows, the steady flow and unsteady flow, the uniform and non-uniform flow, the laminar flow and the turbulent flow, the most important one, the laminar flow in which the particles are having a definite path and the particles are not crossing each other, whereas in the case of turbulent flow, they are not having definite path and the particles are crossing each other. Then we have seen three different type of energies: the kinetic energy, the potential energy, and the pressure energy, and their three respective heads: the kinetic head or the velocity head, then the potential head and the pressure head, and their three expressions. The kinetic head is given by v square upon 2g, the potential head by capital Z, and the pressure head by P upon W. Then we have seen their combined expression. Adding all these three, we will get the expression for the total head. Then we saw the Bernoulli's theorem, that in a particular from one section to the another section in an incompressible fluid, the total energy remains constant, and its expression, the kinetic head plus potential head plus pressure head, it is always constant according to Bernoulli's theorem. And then we have seen three different regarding the assumptions made by Bernoulli's and certain limitations also. Finally, we have seen the applications, three different type of applications of Bernoulli's theorem. The first one, the Venturi meter, having three parts: the converging part, the throat, and the diverging part. Then the Orifice meter, a simple plate which is used to calculate the discharge through a pipeline. Venturi meter once again can be used for calculating the discharge. And finally, we have seen regarding the Pitot tube, a very simple L-shaped instrument which can be used to calculate the velocity through any stream or through in air also. So, this is all regarding our today's lecture of Bernoulli's theorem and its applications. Thank you very much.